Thank you for that last question. To agree is polite, but to disagree is usually much more interesting. Our final paper this afternoon is entitled The Dynamic Response Behaviour of Multi-Legged Articulated Tower with and without TMD.
So today I'm going to give a presentation on the dynamic response of smooth behavior of multi-leg articulate tower with and without TMD. So I'll give you an idea about what is an articulate tower and the TMD. So the main objective is, like we have covered a few of the literature reviews, and we found that very few studies have been done on this articulate towers and also the TMD. TMD is a tuned mass damper actually, a single pendulum. And to conduct the detailed experimental studies on this, and the responses have been calculated. So this is an articulate tower. It's a tower. This is a single leg articulate tower actually. Single leg articulate tower is a tower which is a buoyant. It is a very buoyancy chamber and a ballast chamber, and the bottom portion is actually connected to the base with a universal joint. Now a universal joint is a joint which helps to rotate in all the degrees of freedom. I mean, can move in all directions. So, yeah, the material I have used for my experiment is actually perspex. So, since I carried out for a regular waves and the wave approach angles of 0 degree, the regular waves of wave height 6 cm, 9 cm, 12 cm, and 50 cm from the varying wave periods of 1.3 second, 1.5 second, 1.7 second, and 1.9 seconds are considered. Though in some cases 1.9 has been neglected because the structure is pretty unstable at that wave heights. So this is my model. Initially which I showed is actually single leg. In this case we have 4 legs. All the 4 legs are done to the base with the universal joint, and the deck is free to move along with the wave like a small it can blend with the wave motion. So the stresses developed in the structure is very less compared to a fixed structure. Yeah, the TMD is a small simple pendulum which is not much used in the offshore industry, but you can see in Type 101 building, and this is a very good example for this small pendulum. It's a small pendulum with a mass which can be tuned, can be changed, and normally we take 1/10 of the whole structure just to avoid the resonance effect onto the structure. So this is a picture of my model, and you can see strain gauges attached to the legs, and an accelerometer will be attached to the center. So this is perspex material fixed with the universal joint. Yeah. So this is the universal joint which helps in moving the leg in all directions. And as you can see, this is the stationary position. The TMD is just on the side. When I started the experiment and the waves are being run, you can see the TMD moves, swings, and the movement of the structure is, the energy is transferred to us by inertia to the TMD, and thus the structure comes to a stable position quicker than the one without a TMD. And I did the experiment with no ballasting, water ballasting, and sand ballasting, check which is more which is having more the less bending moment is there in this structure. So for perspex tubes, the same thing I have explained, 100 millimeter diameter and 1.15 meter long, and top of each leg is covered with the perspex plate and the ball joint. So universal joint is covered to allow the undamaged movement. Top deck consists of a perspex plate of the shape of 0.7 meter. Column spacing is maintained as 0.3 meters. So three pairs of resistance type half-bridge strain gauges are fixed on the legs of the articulate tower, and the typical strain gauges which usually takes readings of strain gauges, and this accelerometer which is fixed on top, and each accelerometer measures the movement or acceleration of the deck in each direction, X, Y and Z. And we have the output on a Catman Express similar software for taking the outputs of the strain gauge and accelerometers. And this is the plume where I was working, and it is a 2-meter plume, and this is a piston which pushes the wave. It's a piston type of wave maker, and this pushes the water to create the particular required wave height and wave period. We countercheck with using a wave probe, as you can see here, it is attached on the carriage, and you can calculate the check whether the wave generated is the same as we have given. And this is a mathematical formulation, the equation of motion of the tower and the small inclination, where you can see J55 is the coefficient of mass moment of inertia, and J55 is the coefficient of added mass moment of inertia, B55 is the damping coefficient, and C55 is the hydrodynamic restoring coefficient. And from that we can come to the moment development of the structure. This is for checking the natural frequency of the articulate tower, whether the frequency is coming in which is coming. We have to check whether the frequency is in resonance with the tuned mass damper. If it comes, then the structure may collapse. So for that we have to calculate the frequency of the articulate tower. It can be seen that the MLAT has a large hydrostatic restoring coefficient. If this leads to this low natural frequency, this can be achieved by increasing the coefficient of mass, as you can see here. The coefficient of mass can be and the added mass of the moment of inertia. This research enhances the possibilities of achieving this through TMD. By using TMD, we can reduce the frequency generated in the tower. So the research and discussion. So these are the serious set of experiments that are conducted with ballast and without ballast, with sand and water ballast, and all the cases with and without TMD. So the result is like this. As you can, there are some variation in the case of some, say for example, not TMD is usually in every case I got not TMD as the highest value, but in certain cases 250 gram just comes more than the not TMD case. We are actually researching, trying to find on analytically by using ANSYS Aqua software, so that we will have a detailed study on it later on in the topic. And this one, it clearly shows not TMD is having more bending moment on the structure. This is along the height of the leg, 1.2 meter is the length of the length of the leg of the structure, and you can easily see that the bending moment is somewhat higher on the 1/3 or near to the water. 0.9 was the water depth, so in that area you can see the maximum bending moment, and slowly decreases to 0 to the bottom, and 0 at the bottom. And this is the RAO of sand ballast case, and you see the conclusion is, the RAO bending moment of sand ballast cases are almost similar. The RAOs are similar for each case, like 6 cm or 5 cm, whatever is almost same. The bending moment decreases with the increase in mass of TMD and with the increase in frequency as well. However, along the frequency 150 gram, TMD is showing higher value than the other cases of TMD, except in 15 cm case. The lowest BM in response is shown by 250 gram of TMD. And this is a case of water ballast, slightly different because there is another added effect of sloshing. RAO BM response does not show a similar shape as being in the case of the sand ballast. This shall be attributed to sloshing within the hollow legs of the tank. The ballasting chamber is not completely filled with water. So sloshing is there, so slight variation in the BM is there. And this is for the no ballast case. RAO BM response show higher values for no ballast case when compared to sand and water. However, least response is seen in the TMD. So we can see that when the mass increases, mass of TMD increases, the RAO of the BM is reduced. This is a deck acceleration graph, one of the graphs. You can see the acceleration is reduced when compared to no TMD cases. Conclusions. The bending moment is maximum at the 1/3 of the height of the structure. The bending moment along the tower and deck acceleration increases with wave height by providing buoyancy chambers at the appropriate locations. This sensitivity to the increase in response can be controlled. The bending moment and the deck acceleration decreases with the increase in wave frequency. The bending moment of the structure decreases with the increase in the mass of TMD. However, in the case of 150 gram of TMD, the response is higher. This is due to the frequency range close to the fundamental frequency of the tower. That we have calculated mathematically and found that when you use 1 milligram of TMD, the frequency of the TMD is very close to the frequency of the structure. So it's nearing to the resonance, and hence the bending moment is slightly higher for the case. Thank you.
Are there any questions?
Hi, thank you. Very interesting experiment. How did you calculate the bending moments? Could you?
From the strain gauges? Yeah, the bending moment.
Strain gauge gives you stress or strain.
Strain, yeah. From then you can calculate the bending moment value. M by I is equal to the equation. Bending moment equation. We can calculate the moment.
So did you have strain gauges on both sides of the?
Oh no. It's actually along the leg, and we have got a set of many readings. So I can show it in the presentation. There is a lot of experience that we have done.
Right. So
and we set the maximum strain obtained from the series of waves. So we take the typical value of that.
So you had an array of strain gauges.
Exactly. Yeah. We have provided the strain gauges on different intervals along the leg, and found out in a particular point we get a series of readings. In that series we take the maximum value. So these are actually maximum possible bending moment on the structure. It must not be always the same, but it can be.
Yeah.
You said that 1/3 is the maximum bending moment point, 1/3 of the height
Of the structure.
Is it possible to calculate numerically and compare it?
Actually, the modeling part is over in aqua analysis.
No, forget about all these packages.
Yes.
Can you calculate numerically the bending moment and find that it is matching with the 1/3 of the whatever your result?
Yes, sir. We can. Ultimately, we can do it.
Then why don't you do that? Are you planning to do?
Yes, sir. I have not completed my work yet. This is the only experimental part I am pursuing here.
Okay.